Let's now take more examples of organic reactions to illustrate the concept or the idea of using curly arrows to indicate electron movement, the idea of using curved arrows to be able to draw possible mechanisms or how reactions take place. For example, a reaction between this alkene and the chlorine molecule, you will notice for sure that this is a typical example of an electrophilic addition reaction of alkenes, reaction between the alkene and the halogen. Now, in order to be able to write a product, we need to understand that the alkene behaves as a nucleophile in this case, so it reacts with the electrophile. And again, this is not an example of an organic reaction where oppositely charged substances or intermediates attract with each other. This is an example where a HOMO, basically a filled orbital, overlaps with an empty orbital from the halogen. This is an example of a HOMO-LOMO interaction, if you like. Now what we need to do is we need to indicate electron movement. We need to draw an arrow from the middle of the carbon-carbon double bond, and we say from the middle of that carbon-carbon double bond because it is a pi bond that's about to break. A pi bond that's about to break, and when the pi bond is broken, 2 electrons are released, and these 2 electrons will then be used to make a bond between one of these carbons and chlorine. So let's take the arrow from the carbon-carbon double bond to one of the halogens. If you notice again, the strict movement of that arrow is from the middle of that carbon-carbon double bond, because this is indicative of a breakage of a pi bond, okay, the bond that was that's formed or that's used to make a pi bond between these 2 carbon atoms. The 2 electrons are now being used to make a bond between one of these carbons and the chlorine, one of the chlorine atoms. Now chlorine, again, because it's in group 7a, it has 1 valence electrons. Halogens can only make 1 bond, so they have to keep that all the time according to valency rules. Therefore, that Cl-Cl bond must break at the same time. So therefore, we get something like that. And if you look at that arrow, the arrow originates from the middle of that Cl-Cl bond, which is indicative of a breakage of that Cl-Cl bond. Now the 2 electrons that have been released as a result will now go to the other chlorine atom. So we get something like this as an intermediate. It's the chloronium ion actually, plus the chloride ion, and we will see details of this type of electrophilic addition reactions when we talk about alkenes. Now, another example will be if you take, for example, this alcohol and you react this with sulfuric acid. So alcohols react with strong acid. They get protonated. So how is that so? Well, the lone pair from oxygen is used to make a bond between that oxygen and the proton, if you like, the positively charged hydrogen due to inductive effect. And we know that acids anyway are proton donors by definition. And this HO bond, this is actually polar or polarized because of the difference in electronegativity between oxygen and hydrogen. Oxygen obviously is more electronegative than hydrogen. Therefore, oxygen has a negatively charged delta, if you like. Hydrogen has a positively charged delta. Therefore, hydrogen is susceptible to nucleophilic attack, and the nucleophile in this case will be the lone pair from oxygen. So we use an arrow from oxygen, which indicates movement of 2 electrons coming from oxygen because it is the nucleophile in this case. And we've seen that already before, that alcohols behave as neutral nucleophiles because they have lone pairs. Okay, so the lone pair is now used to make a bond between oxygen and hydrogen. So that's the origin of the arrow. This is the destination of the arrow. It's hitting hydrogen. Now, hydrogen cannot make more than one bond according to the Duet rule. And therefore, this hydrogen-oxygen bond must break simultaneously. And if it does, this bond is broken. If it does, now we make a double bond here. And at the same time, this sulfur-oxygen bond breaks. You see this beautiful electron movement, if you like. A bond between oxygen and hydrogen is formed. It's a doubly headed arrow to indicate movement of two electrons from oxygen going to hydrogen. This hydrogen-oxygen bond is being broken. This oxygen, there's a double bond that has been formed between oxygen and sulfur, and the double bond between sulfur and oxygen has been broken at the same time. So what we can do now is we can write the resultant products. So something like that. Are produced. Now, if you look at oxygen now, it has a formal charge of 0. That's because it has 6 valence electrons. And if you subtract that 6 valence electrons in this structure from the number of valence electrons of oxygen in the free state, you get a formal charge of 0. The number of valence electrons in this case are actually 5. If you subtract 5 from 6, which is the usual number of valence electrons of oxygen in the free state, you get a +1, so that the formal charge of oxygen in this protonated intermediate is positive. So we get also the hydrogen sulfate, HSO4-, which is the conjugate base of sulfuric acid as a result of the donation of a proton. So let's take now another example. Of a nucleophile electrophile attack. So this is a reaction between dimethyl sulfide and bromine. Now, sulfides behave as nucleophiles because they have lone pairs. Okay, so if you look at sulfur, it has 2 lone pairs, so therefore it can function as a nucleophile. Halogens, we've seen them before, they behave as electrophiles because they have an empty sigma star orbital. They have, if you like, a LUMO orbital, an unoccupied or an empty orbital, which can be used to interact with HOMO orbitals coming from nucleophile. So again, this is an example between a reaction of a HOMO orbital and a LUMO orbital, a filled orbital, and an unfilled orbital or empty sigma star orbital in the halogen. So we can indicate this using electron movement of this type. Now this arrow indicates movement of 2 electrons coming from sulfur, and these 2 electrons are now being used to make a bond between sulfur and bromine. But also we have to break this BR-BR bond at the same time, because halogens can only make 1 bond and not more than 1 bond. So the products of this reaction will be these. If you look at these 2 products, you will notice that there is a positive charge on sulfur, and that's because the formal charge is actually +1. There are 5 valence electrons around sulfur in this intermediate. If you subtract 5 from 6, which is the number of valence electrons of sulfur in the free state, you get a +1 formal charge, and that's exactly why sulfur is positively charged. Now, what's left of the bromine molecule, if you like, or the bromine molecule as a result of breakage of that BR-BR bond is the bromide ion itself. So these are the 2 products of this reaction. These additional 3 examples illustrate the use, if you like, of Cayley arrows to to indicate electron movement in these types of polar reactions, which constitute the vast majority of organic reactions. And actually the reactions between filled orbitals, or HOMO orbitals if you like, and unfilled orbitals or empty LUMO orbitals also constitute the majority of organic reactions.